for unimolecular nucleophilic substitution. Keep in mind this reaction is in competition with E1. The mechanism starts when the leaving group breaks away from the alkyl chain, taking the electrons with it, leaving carbon with a positive charge. The Cl- dissolves in solution as an unreactive spectator ion, and we have a carbocation intermediate. This is the clue for an SN1 reaction, a carbocation intermediate that is slow to form and the rate-determining step of the reaction. The solvent acting as a nucleophile in a solvolysis reaction will use its lone electrons to attack that positive charge, forming a bond between the nucleophile and carbocation. The incoming oxygen now has 3 bonds and 1 lone pair for a positive charge, which we get rid of when another solvent molecule uses its electrons to deprotonate the oxygen by taking the hydrogen and giving it back its electrons to give me a final product. If your professor wants side products, you can also show the protonated solvent molecule as a CH3OH2+, with its counter ion, the leaving group, as Cl-. The clues to recognize that an SO1 reaction takes place is as follows: carbocation intermediate as the rate-determining slow step, and a solvent nucleophile attached where the leaving group used to be. SN2 stands for bimolecular nucleophilic substitution, where bimolecular is 2 molecules reacting at the same time in a one-step, no intermediate reaction. For this reaction, we have a primary leaving group reacting with NaSH in a polar aprotic solvent, DMSO. Anytime you see Na, recognize the spectator positive ion to give us a negative S, which is a good nucleophile. This is a fast reaction because we're not waiting for a carbocation to form. Instead, the nucleophile will take its lone electrons, directly attack the carbon holding the leaving group to kick that out, so that in one single step, we get the entire product. SH is now attached where bromine leaving group used to be, and the leaving group is floating around somewhere in solution. This product is achiral, but in the case of a chiral starting molecule, you would get an inversion of the initial configuration for SN2 reactions. The clues for this reaction are as follows. We have absolutely no carbocation intermediate. This is a fast reaction that happens in one step, and the fact that the nucleophile sits on the carbon where the leaving group used to be. E1 stands for unimolecular beta elimination. This is similar to the SN1 reaction and is often in competition. In fact, we'll demonstrate this reaction using the same starting molecule and reagent. The only difference is that we'll add heat, because this will help us favor elimination over substitution. The mechanism begins in the same way, where the leaving group will grab the electrons binding it to carbon and break away to give us a carbocation intermediate. This is the rate-determining slow step of the reaction, where the leaving group just wanders away somewhere in solution. For elimination, instead of a solvolysis where the nucleophile attacks the carbocation directly, the nucleophile is looking for a beta hydrogen, a hydrogen that sits on the carbon next to the carbocation, and it'll use its electrons to pluck off that hydrogen. The electrons that bind hydrogen to carbon will stay on the molecule and collapse towards the positive charge to give us our final product, which has a pi bond between the alpha and beta carbon. The clues that an E1 reaction took place is as follows. 1. You have a carbocation intermediate. And 2. You have a pi bond between the alpha and beta carbon. E2 reaction is a bimolecular beta elimination. Bi tells us 2 molecules reacting at the same time. That means no intermediate for a fast one-step reaction. For this E2 reaction, we'll look at a secondary leaving group reacting with NaOCH3 and CH3OH, recognizing that Na is a positive spectator, giving us a negative base, in this case CH3O- or methoxide. We'll add in heat to help stabilize the pi bond formation intermediates. This will favor an E2 over SN2 reaction. Like the E1 reaction, we're not attacking directly. Instead, we're looking for the most substituted beta hydrogen. so that the base can grab the hydrogen and pull it off the molecule. This will cause the electrons between hydrogen and the carbon to collapse in the direction of the leaving group, kicking out the leaving group, so that this is a one-step, absolutely no intermediate reaction to give us the product. The product is a pi bond between the alpha and more substituted beta carbon for the Zaitsev elimination. The clues that this reaction took place includes absolutely no carbocation intermediate because we have a strong attacker and a fast one-step reaction. Our second clue is a pi bond between the alpha and more substituted beta carbon. Do you need to see these reactions in more detail? I've broken down everything regarding substitution elimination reactions in a 20+ video series, along with a practice quiz and cheat sheet, which you can find on my website. Click the link in the description or visit leahforsci.com/substitution-elimination. In order to master these reactions, you first have to learn how to evaluate the 4 criteria that will help you determine if substitution or elimination will take place. This includes analyzing the alkyl chain, the incoming nucleophile or base, the solvent the reaction takes place in, and evaluating the leaving group. The series